TTFT versus mainstream physics, real predictions or just numerology. I want to do something most so-called theories of everything never dare to do, put the predictions on the table. No hand waving, no free parameters, no, it's too hard to calculate. I'll walk through what toroidal torsion field theory, TTFT, actually says about the fine structure constant and the weak mixing angle, the full standard model mass spectrum and neutrino masses, and even cosmology, dark energy, tensor tilt, and CMB anomalies. And for each one, I'll tell you whether mainstream physics can already predict it, or whether TTFT is stepping into genuinely new territory. What TTFT is trying to do. Before we get to numbers, let me fix the playing field. TTFT starts from 4 geometric ideas. 1. There's a conserved flow on a compact 3-dimensional manifold. All fields are torsion and curvature of a Cartan connection on that manifold. 2. The spatial manifold is a flat 3 torus, which you can picture as a cube with opposite faces glued together. 3. The dominant vacuum configuration balances torsion and curvature. Their norms are equal. In symbols, double bar t squared equals double bar r squared. 4. The torsion spectrum has a special phi-stable eigenmode controlled by the golden ratio, phi, that anchors all dimensionless scales. From just that, TTFT claims it can derive the inverse fine structure constant, often written alpha inverse, the weak mixing angle, sine squared theta w, Newton's constant g, the dark energy equation of state parameter WDE, the tensor spectral index n sub t, and the extra effective number of relativistic species, delta and f. On top of that, it claims the whole fermion mass hierarchy, neutrino masses, and the lepton G-2 anomalies, plus concrete cosmological signatures of a 3 torus universe. Mainstream physics simply does not do this. It fits those numbers, it runs them, it interprets them, but it doesn't derive them. Fundamental constants, same targets, different game. Let's start with the poster child, the fine structure constant alpha. Mainstream quantum electrodynamics says, give me alpha at one scale and I'll tell you how it runs. But that initial value is just an input. TTFT says no, the effective U1 generator is a specific torsion current, J1 on the 3 torus, normalized so that its circulation around a fundamental cycle is 1. The inverse coupling is just its L2 norm. Alpha inverse equals 4 pi times the L2 norm of J1 squared. No adjustable factors, no renormalization scheme choices. You discretize the 3 torus, compute the lowest harmonic torsion mode numerically, refine the lattice, and extrapolate. The prediction comes out as alpha inverse from TTFT equals 137.03629 plus or minus 0.00054. The code data value is approximately 137.035999, so we're off by about 2 parts per million with an explicitly tracked numerical error budget. This is a case where TTFT goes after the same observable mainstream uses, but as a pure geometric invariant, not a fitted input. Weak mixing angle, sine squared theta w. TTFT has a genus 1 current J1 and a genus 2 triplet of currents J2, forming an SU2 algebra. Their norms set the relative couplings. G1 inverse squared is proportional to the norm of J1 squared, and G2 inverse squared is proportional to the norm of J2 squared. Then the usual electroweak relation, sine squared theta w equals G1 squared over G1 squared plus G2 squared, becomes purely geometric. Numerically, at the same lattice resolution, TTFT gives sine squared theta w equals 0.23136 plus or minus 0.00017. The particle data group gives about 0.2315 plus or minus 0.0002. Again, same target as mainstream, but now as a torsion geometry ratio instead of a fitted electroweak parameter. Newton's constant G and dark energy equation of state WDE. In general relativity, G and the cosmological constant are just constants in the field equations. TTFT instead has only the torsion and curvature action on the compact 3 torus. Integrating out high-frequency torsion fluctuations and matching to an emergent Einstein-Hilbert term gives you an effective gravitational coupling. In the TTFT prediction paper, the value quoted from the dedicated TTFT gravity work is G from TTFT equals 6.1 times 10 to the minus 11, plus or minus 0.5 times 10 to the minus 11 in SI units. so about 8.5% low compared with 6.674 times 10 to the minus 11. This is a rougher but still non-trivial first principles prediction. The more striking cosmological quantity is the dark energy equation of state. TTFT's vacuum is a torsion curvature condensate obeying the equal norm condition. The expectation value of T squared equals the expectation value of R squared. And the renormalization group fixed point selects the golden ratio phi as the torsion curvature scale ratio. After including nonlinear mixing and loop corrections, TTFT gets WDE equals minus 1.0263 plus or minus 0.0067. So slightly phantom, less than minus 1 but without scalar ghosts, the effect comes from geometric torsion curvature feedback, not a negative kinetic term. Lambda CDM, of course, is just W equals minus 1 by construction. Finally, still in the constants bucket, TTFT predicts the tensor spectral index and a small extra radiation component. The torsion spectrum has an anomalous dimension. From the phi stable scaling, TTFT finds an effective tensor tilt. N sub t from TTFT equals minus 0.764 plus or minus 0.150. That's a strongly red tensor spectrum, very different from slow roll inflation's tiny negative value. It implies CMB scale gravitational waves could be visible, while high-frequency primordial backgrounds in the LIGO band are essentially absent. On top of that, the discrete torsion modes behave as an extra relativistic component in the early universe. Counting modes and tracking their thermal history gives delta NF from TTFT equals 0.045 plus or minus 0.015. That's small enough to be consistent with Planck, but big enough for CMB-S4 to test. Now for particle physics. This is where TTFT goes well beyond what mainstream currently calculates. The torsion Laplacian on the 3 torus has a discrete phi recursive spectrum. When you work at high lattice resolutions and look for eigenmodes that are stable under the phi twist, you find a small cluster of phi stable modes with continuum mass m infinity approximately 3.4085 in dimensionless units. After calibrating the internal length scale using the torsion gravity relation, that continuum eigenvalue corresponds to a physical mass scale, m root approximately 0.503 mega electron volts. Without using the electron mass as input, so TTFT's raw spectrum naturally lives right where the electron sits. Mass formula mf equals m root times phi to the n phi times cg. The full mass hierarchy does not come from higher eigenvalues, those are too dense and messy. Instead, TTFT uses the internal phi recursion structure. Each fermion is associated with a genus G, 1 for leptons, 2 for weak doublets, 3 for quarks, an integer phi index n phi, and an order 1 genus-dependent shape factor Cg from torsion overlaps. The mass formula is m of g and n phi equals m root times phi to the n phi times Cg. From the lattice data, the phi indices that line up with the observed spectrum are n phi equals 0, 11, 22, 8, 9, 19, 20, 30, and 31, mapped appropriately to the electron, muon, tau, and the quarks. The shape factors are near 1. With no free parameters besides the overall m root scale, which itself came from the torsion spectrum and from G TTFT reproduces, the electron, muon, and tau, and all 6 quark masses, with typical errors from a few percent up to about 15% for the bottom quark and the tau lepton. And because the only inputs are the integer phi index and the genus label, extending the spectrum is straightforward. Choosing a new pair, G and n phi, immediately gives a concrete mass prediction for any hypothetical particle sitting on that rung of the phi tower. Neutrinos nearly massless in a sharp bound. TTFT's neutrino story is sharp and very different from many model building games. Neutrinos share the same phi indices as their charged partners, 0, 11, and 22, but their genus 1 shape factor vanishes in the continuum limit. They couple differently to the torsion background, essentially decoupling from the mass-generating piece. The only contributions come from very small cross-genus mixing terms. The result is a hard upper bound. The electron, muon, and tau neutrino masses are all less than 10 to the minus 4 electron volts. Not just light, but essentially as light as cosmology allows. So if future experiments pin neutrino masses at, say, 0.05 electron volts, TTFT as formulated here is dead. Muon and tau G-2, genus 2 overlaps. The same torsion modes that generate the masses also generate anomalous magnetic moments via overlap integrals with the genus 2 torsion background. For the muon, TTFT computes a parameter-free anomaly. Delta mu from TTFT is about 2.48 times 10 to the minus 9, with an uncertainty of 0.22 times 10 to the minus 9, which lines up with the current Fermilab and Brookhaven discrepancy. For the tau, delta tau from TTFT is approximately 2.5 times 10 to the minus 9, with a 20% uncertainty. Current tau G-2 constraints are way too weak, but if a future tau factory reaches 10 to the minus 9 sensitivity and sees nothing at that level, the genus 2 overlap picture is in trouble. Confinement and proton mass bound from topology. Confinement in TTFT is not a running coupling story, it is global topology. Torsion flux through the three independent 2 cycles of the 3 torus is quantized. A single quark carries a non-zero flux vector, which violates global closure. Only combinations with total flux 0 are allowed. The sum of all quark flux vectors must be 0. That immediately reproduces the no-free quarks, only mesons and baryons structure. Combining this with the quark masses from the phi tower and a geometric flux energy gives a proton mass band, roughly 880 mega-electron-volts less than or equal to MP less than or equal to 960 mega-electron-volts, which contains the observed 938 mega-electron-volts. Again, not perfect, but non-trivial for a geometry-only theory. Cosmology and topology, where TTFT really leaves the standard model. With the 3 torus as the actual spatial topology, TTFT predicts specific CMB and large-scale signatures, independent of inflation details. First, there is an infrared cutoff. Modes with wavelength larger than the fundamental domain simply do not exist. That naturally suppresses the lowest multipoles C2 and C3. Second, the 3 cycles pick out preferred directions, generating a hemispherical power asymmetry of order 7%. Third, helical torsion induces parity violating TB and EB correlations at the 10 to the minus 3 level compared to EE. Each of these individually is not decisive, but the combination, low quadrupole hemispherical asymmetry aligned with a principal cycle, and TB and EB at the predicted amplitude, is a fairly sharp signature of a toroidal universe with a torsion condensate. Growth index gamma and S8 tension. TTFT's vacuum also changes late time structure growth. With WDE equals minus 1.026 and a small torsion radiation component, the growth index becomes gamma from TTFT approximately 0.553 plus or minus 0.005 instead of the lambda CDM value 0.545. That slows growth slightly, suppressing sigma 8 by about 1.4%. Translating to the lensing parameter S8, TTFT predicts S8 from TTFT approximately 0.80 plus or minus 0.02, which sits between Planck's roughly 0.83 and Lensing's roughly 0.76 to 0.79. So it naturally eases the S8 tension, again with no new parameters, just the same torsion condensate that produced WDE and N sub T. Falsifiability and wrap-up. All of this would be meaningless if the theory could just bend to fit anything. The predictions paper explicitly pre-registers falsification bands. A few highlights. If future measurements of alpha differ from 137.036 plus or minus 0.075 by more than 5 times 10 to the minus 4, the phi normalized U1 sector is wrong. If sine squared theta W at the z pole leaves the 0.23096 to 0.23176 band, the genus 1 over genus 2 norm ratio is wrong. If neutrino masses turn out to be greater than about 10 to the minus 2 electron volts, the genus 1 massless structure is ruled out. If the muon G-2 converges to the standard model value with no anomaly, TTFT's genus 2 overlap prediction fails. If dark energy W is really approximately minus 1.0 with precision better than 0.01, and the tensor tilt is mild, the whole equal norm and phi fixed point vacuum picture is in serious trouble. And of course, if the universe is not topologically a 3 torus, if CMB and topology searches exclude that, the foundational topology conjecture is simply wrong. So TTFT is either going to be killed or strongly constrained in the next decade by precision alpha and sine squared theta W measurements, mu1 g-2 and perhaps tau g-2, neutrino mass surveys, and Euclid, DAISY, Lightbird, CMB-S4, and CMB topology analyses. That's the point of this episode, to show the full menu of predictions now while they can still be tested. And maybe most importantly, TTFT does not just repackage the constants we already know. It gives explicit parameter-free mass formulas for the actual particles we see, something mainstream physics in its current form simply does not do. So is TTFT just numerology? No, it is not. The chance that all of these constant derivations and cross-linked predictions are just happy coincidences is vanishingly small. Are TTFT's predictions all perfect? Also no. Many of them are still rough estimates, limited mainly by current grid resolution and computational power, and they should sharpen as the numerics improve. But even in this imperfect state, TTFT is already doing something mainstream theories are not. It is giving concrete, parameter-free predictions for particle masses and cosmological observables that the standard model and general relativity simply leave as unexplained inputs.